Hello class, I hope you're having a wonderful day. Today I would like to take a look at one of the inclined plane practice problems from chapter 5. So what I'm going to do is read the problem to you. I'm going to underline important information. Then we will generate a column of knowns and draw a diagram, and then we will calculate the 6 required variables that is listed in the problem. So let's go ahead and get started. A 400 Newton crate begins to slide down an inclined plane that is 41 degrees from the horizontal. The coefficient of kinetic friction between the crate and the inclined plane is 0.53. Draw a diagram, and we're going to calculate these 6 items. So let's go ahead and get started with the column of knowns that is given to us in the problem. The first thing is the weight force due to gravity. So this is identified by F sub g, and it is a negative 400 newtons. Remember, weight force is a vector, and the vector points in the negative y direction. So we have a negative value here. Angle theta, and this is the angle between the inclined plane and the horizontal. This is 41 degrees. And then we have the coefficient of kinetic friction, which is identified by mu sub k, 0.53. Now let's go ahead and draw a simple diagram. So let's first draw the angle. The angle is 41 degrees, and we have a crate on the inclined plane. Just draw a simple crate like that. Now remember from the notes that I gave you, the 6 facts for an object on an inclined plane. Fact number 1 is the weight force points in a negative y direction, and it is perpendicular to the horizontal. So we need to draw this vector right here. Okay, and it is weight force due to gravity, identified by F sub g. So it's perpendicular to the horizontal, so we have a 90-degree angle right here. And F sub g is equal to negative 400 newtons. Now we do not have to put the negative value here since our vector arrow is pointed in a negative y direction. So let's just label this as 400 newtons. Now, since our crate is resting at an angle, it's on an inclined plane, we know that we can break this weight force vector into 2 different vectors, into its x and its y component. Now, the y component of weight force has a negative y component, so it's pointing in the negative y direction, and it is perpendicular to the inclined plane. So right here, it's perpendicular. We have a 90-degree angle here. Let's label this F sub g sub y. And then our x component of vector points in a negative x direction, and it's parallel to the inclined plane. And this is identified by F sub g sub x. And we can project this vector down right here. We're using the head to tail method. We're going to place the tail of the x component of weight force vector on the head of the y component of weight force vector. So using the head to tail method, let's go ahead and label this F sub g sub x. That's my x component of weight force. And we know this creates a 90-degree angle, so we have a right triangle. And one more very important thing about this triangle that we've created with our vectors is the angle between the weight force due to gravity and the y component of weight force. This angle is equal to the angle between the inclined plane and the horizontal. So we have a 41-degree angle here, and we have a 41-degree angle there. Okay? So this is enough to go ahead and get us started right now. In part A, it wants to know what the x component of weight force is. Well, we're looking for this guy, the x component of weight force. And in this triangle, this side, with respect to the 41-degree angle, is the opposite side length. So right there, we're looking for this guy. And so what we have is sine of the angle theta is equal to the opposite side divided by the hypotenuse side. Now I'm going to take my base equation here and adapt it to what we're doing. So I'm going to be a little bit more descriptive here. My opposite side length is my x component of weight force. So I have sine of theta is equal to my x component of weight force divided by the weight force due to gravity. Now we're calculating x component of weight force, so we need to isolate that on one side of the equal sign. So I'm going to multiply both sides of the equal sign by weight force due to gravity, and on the right hand side of the equal sign, weight force due to gravity cancels. So x component of weight force is equal to our weight force due to gravity. We have a negative 400 newtons times sine of 41 degrees. Now go ahead and get out your calculator. Remember, make sure that your calculator is in degree mode, not radian mode. Make sure it's in degree mode right now. So we have negative 400 times sine of 41 degrees. I get negative 262.4 newtons. Okay? All right, we can go ahead and label this in our diagram here.
At this time, we will observe a moment of silence. You may select whether you wish to
There we
reflect,
go. But
meditate,
I'm going to copy this
pray,
value
or engage
next to
in
part A.
disruptive
So remember
silent
part A,
activity.
x component of weight
Okay,
force.
60 seconds.
I have negative
The moment of silence will
262.4
begin now.
newtons. Okay? Part B, it wants us to calculate the y component of weight force. So now we're looking for this vector here. Okay? So my unknown side length here, with respect to the angle 41 degrees, this is the adjacent side length. So since we're looking for the adjacent side length, we're going to be using the trigonometric function cosine. So what I have here is cosine theta is equal to the adjacent side length divided by the hypotenuse side length. Now I'm going to adapt my base equation to my situation, and I'm going to be more descriptive here. I don't just want to leave this adjacent side length. Let's call it the y component of weight force, because that's what we are actually solving for. So cosine theta equals the y component of weight force divided by our weight force due to gravity. So we have y component of weight force is equal to the weight force due to gravity. So I have a negative 400 newtons times cosine of 41 degrees. So negative 400 times cosine of 41 degrees, I have negative 301.8 newtons. So let's go ahead and transfer our calculated value for the y component of weight force to our list over here. So negative 301.8 newtons. And I'm going to label the diagram that we drew. So 301.8 newtons. Right here, my calculated value is negative, okay? But our vector's pointing in the negative y direction, so I do not need to have my negative sign here because I'm showing direction with the vector arrow. Okay? Part C. Okay, on part C it wants to know the normal force. So in our notes, the 6 facts for an object on an inclined plane, we know that the normal force is equal in magnitude to the y component of weight force, but the vector points opposite in direction. Remember, this is called an interaction pair. So normal force identified by F sub n equal in magnitude to the y component of weight force, but opposite in direction. So 301.8 newtons. Okay? Now we need to calculate the kinetic friction force. And so our base equation to calculate this is the coefficient of kinetic friction is equal to the kinetic friction force divided by the normal force applied to the object. So our kinetic coefficient of friction is 0.53. This is equal to our kinetic friction force, which is our unknown, and we're dividing by our normal force applied to the object, 301.8 newtons. So what I'm going to do is multiply both sides of the equal sign by our normal force applied to the object. So this is going to give me the kinetic friction force is equal to the coefficient of kinetic friction, which in this case is 0.53 times 301.8 newtons. So we're going to get 159.9 newtons. Okay. And so we have we have a positive value here. So this vector is pointing up the ramp, and it is parallel to the inclined plane. Let's go ahead and label it. The kinetic friction force is equal to 159.9 newtons. Okay, let's go ahead and label that over here for your answer. Now on part E, it wants us to calculate the net force applied to the object. So in the y direction, we know that our system is in equilibrium. Our y component of weight force and the normal force applied to the object, they are equal in magnitude, but the vectors point opposite in direction. So we have equilibrium. But in the x direction, we do not have equilibrium, okay? Pointing down the ramp, we have 262.4 newtons, and pointing up the ramp, we have 159.9. So the net force in this case is going to be the sum of the forces. So I'm going to use my capital Greek letter sigma here, sum of, so sigma, forces in the x direction. So this is going to be the weight force in the x direction plus the kinetic friction force. Okay? Weight force in the x direction, right over here, we've calculated this, negative 262.4. Remember, the reason it's negative is because the vector is pointing down the ramp. So we have negative 262.4 newtons plus 159.9. So let's go ahead and calculate our net force in the x direction. And I get a negative 102.5 newtons. So my net force So we know that the net force applied to our object is going to be pointing, the vector points down the ramp, and we know that according to Newton's second law of motion, if we have a net force applied to an object, the object will accelerate, and that acceleration vector points in the same direction of the net force vector. So net force right here, negative 102.5 newtons. And now we're going to calculate the acceleration for part F. So according to Newton's second law, we know that the acceleration of an object is directly proportional to the net force applied to the object and inversely proportional to the object's mass. So F net divided by mass. So we calculated the net force applied to the object. this is a negative 102.5 newtons. And we're dividing this by the mass of the object. Well, right now we don't have the mass of the object, but we know that the weight force due to gravity is equal to the product of the object's mass and the acceleration due to gravity. So we have the weight force, which is negative 400 newtons, and we know the acceleration due to gravity is negative 9.8 meters per second squared. We're looking for this guy. So my mass is equal to the weight force divided by the acceleration due to gravity. My weight force, negative 400 newtons, divided by negative 9.8 meters per second squared. This is going to give me 40.86 kilograms, okay? Now I really want to take a look at the units here. We know that 1 Newton is equal to a kilogram meter per second squared, and we're dividing by meters per second squared. Let's go ahead and remember our old algebra rule that tells us whenever we divide fractions, it's like multiplying by the inverse of the denominator. So what I have here is kilogram meters per second squared multiplied by second squared over meters. And you can see that meters cancels, our second squared cancels, leaving us with units of kilograms. That's how I'm getting kilograms right here. So we're going to divide by 40.86 kilograms, okay? And I get 2.51, a negative 2.51 meters per second squared, okay? Now, what I want to do to be more specific in this situation is describe the direction of acceleration. Now, we can say acceleration of the crate is equal to negative 2.51 meters per second squared. To be more specific, what we could say is the acceleration of the crate is equal to 2.51 meters per second squared down the ramp. Okay, we can say either one because they're actually both 100% correct, but it's just how you describe it to show direction, okay? So to fill in my answer over here for part F, I'm going to say 2.51 meters per second squared down the ramp, okay? Well, I hope this answers some questions, me working through this problem with you. If you're having any trouble or you have any questions or anything, please give me a call or send me an email. I'd be more than happy to help you. I hope you have a wonderful day.